Good afternoon. Good afternoon, everybody. Come on in. There's a few seats still towards the front up here. I see Keith's holding a few. Good afternoon. Welcome, everyone, to the 100 Years of Cryosphere session, kicking off our AGU Centennial Celebration for the Cryosphere. We've got a wonderful speaker and panel program lined up for you, following on the great Nye lecture and honored members' presentations in advance of our Cryosphere committee, our Cryosphere section meeting and reception just following this session. Our focus here today is a bit retrospective. We're, as I said, kicking off the AGU Centennial Celebration with a thematic exploration of the past century of cryospheric science. Though our current pace of discovery and understanding seems to be rapid and accelerating, it's instructive, I think, for us to reflect on the foundations of our science to lend some context and acknowledge the legacy back to a time before computers and before television, before the World Wide Web, instant communications, and the satellite perspectives. We come from this era. The narratives of this past century comprise a rich tapestry of experience, textured with personal struggles and victories, collaborations, competitions, comradeship, and conflicts. Tightly woven, we must remember, with adjacent disciplines and pursuits. It's not always pure science that drives us to study the cryosphere. It's really a human and natural history that provides a context for understanding our current state of knowledge and to imagine and build our futures. So it's within this context that we start to celebrate our 100-year retrospective, both for the AGU community in general and for us in the Cryosphere section. I want to start by thanking my co-conveners, Andy Barrett up here, Emilio Mateo, and Laura Koenig. And I really want to extend a particularly hearty thanks to our presenters and panelists for their enthusiasm and their participation in this cool event. We'll start with 3 presentations exploring the history and development of cryospheric science from expedition and field science through new spatial perspectives enabled by remote sensing and modeling to the sometimes staccato evolution of our state of knowledge through shifts and paradigms. Our speakers will proceed in sequence, after which we'll convene a discussion panel moderated by Dr. Laura Koenig, who will introduce our 3 additional panelists. First up, we'll start with Dr. Matthew Sturm, who has been a pioneer and leader in ice and snow science. He's conducted numerous extended field expeditions in the Arctic through his long career at the U.S. Army Cold Regions Research and Engineering Lab, and now at the University of Alaska Fairbanks Geophysical Institute. Following Dr. Sturm will be Dr. Waleed Abdelhadi, Director of the Cooperative Institute for Research and Environmental Sciences at the University of Colorado, former NASA Chief Scientist and Cryosphere Program Manager. And he has a long career of being a lauded leader and enabler of measurement, modeling, and remote sensing in the earth science broadly and in the cryosphere in particular. We'll wrap up our presentations with Dr. Richard Alley, the Evan Pugh Professor of Geosciences at Penn State. He's got a great gift of translating his groundbreaking research into abrupt climate shifts and the dynamics of the big ice sheets for broad audience, including strict disciplinarians, broader interdisciplinarians, policymakers, and the general public. It's really, I think, a great lineup. I'm excited for the discussions to follow, and I want to thank all of you for being here, packed in here at this tiny room. And thank you for your participation, and I look forward to your questions to our panel as we move forward. With great pleasure, I welcome Dr. Matthew Sturm.
Thanks, Jeff. Thank you, Jeff, for inviting me. My wife understands that I'm very bad at following instructions, so I'm going back a lot further than 100 years. As the centennial celebration of the AGU and the cryospheric section begins, we find a cryosphere undergoing dramatic changes posing potentially existential threats to humanity. This is an exceptionally exciting time to be a cryospheric scientist, but also one that's stressful. For we are being asked questions whose answers could well be essential to the survival of humanity. Whoops, the arrow. What makes it go forward? This one? Whoop. Oh, we're too far forward now. There we go. At such a moment in time, we would do well to listen to Abraham Lincoln when he said, if we could first know where we are and whither we are tending, we could then better judge what to do and how to do it. Lincoln delivered these powerful words in 1858 in his House Divided speech. Today, 160 years later, when it comes to climate change and what to do about it, in the U.S., we are still a House Divided. But in following Lincoln's dictum, I would argue that to know where we are now, we must know from where we came. That's the journey I've been asked to tell today. 20 minutes is far too short a time to trace this journey, a journey marked by frostbite, crushed ships, mind-numbing blizzards, aurora starvation, and cannibalism. So like the great polar explorer Amundsen, in preparing this talk, I've had to ruthlessly kill any dog that couldn't pull. Sadly then, I've had to leave much rich material out, but I hope what remains tells of a great journey, one that takes place in 3 acts. Act 1, the needle and the north. Before the cryospheric science could ever begin, humans had to learn how to survive in the snow and the wind, how to thread the maze of the sea ice, and how to avoid freezing to death during an ice age. The last requires weatherproof clothing. That story starts 27,000 years ago and literally balances on the point of a needle, an eyed needle. Until this tiny tool was invented, sewn weatherproof clothing could not be made. Eyed needles date back 35,000 years, and carved bone figurines from Siberia showing weatherproof suits complete with snug-fitting hoods have been found dating back 24,000 years. Armed with fur clothing, the record suggests these hardy folks tried to move into Siberia, were pushed back by the bitter conditions of the last glacial maximum, then tried again about 18,000 years ago with better success. They arrived in Alaska wearing furs like this around 12,000 years ago. One of the earliest locations they occupied in Alaska was this, the Mesa site, north of the Brooks Range. I have stood there in the dead of winter and wondered how any human could successfully have lived there, but they did. Because bone and stone make up most of the archaeological record, with soft materials like fur, leather, and wood rarely preserved, we have to turn to Otzi, shown here, the Iceman, to better understand paleopolar clothing. He was found melting out of a glacier in 1991, but lived about 5,000 years ago. He also wore fur and skin clothing sewn with an eyed needle. He had a parka made of straw and a brass axe that I, at least fancy, he used to cut steps in the ice. He also had snowshoes, suggesting an intimate understanding of cryospheric things like snow density and bearing capacity. So Act 1 closes with Eurasians dressed in weatherproof clothing, armed with a variety of specialized cryospheric tools, working their way down the Alaskan coast in boats, or marching through the barren, cold mountain corridors between the Cordilleran and the Laurentide ice sheets. They will populate all of the Western Hemisphere, but a few small bands will stay in the north, contending with the snow and the ice. About 1000 AD, some of these bands, called the Thule Eskimos, will start spreading east towards Greenland and Baffin Island, arriving there just in time to meet the Westerners coming west. So what do these people know about the cryosphere? Their tools tell the story. Goggles indicate they understood snow albedo quite well. Exchangeable bone and ivory sled runners tell of knowledge of snow friction and temperature. Ice crampons tell us that they spent considerable time on the sea ice and on lake ice. And bone knives tell of an understanding of some of the molecular properties of snow. As a collector and builder of snow knives, I find these latter relics extremely telling. These northern people were not only aware of snow sintering itself, but I suspect had worked out how temperature, pulverization, and time controlled the process. knowledge we've had to rediscover in the last 4 decades. We might be tempted to discount this paleocryospheric information as not being part of the corpus of our knowledge, but as we'll see in Act 2, it was those Western expeditions, even science expeditions, that talked to the indigenous people and adopted their tech that generally proved the most successful and least fatal. What was the motivation of these ancestors? Personal survival. Act 2, greed and empire. By 1520, with Magellan having successfully circumnavigated the Earth, it was widely recognized that a great deal of money could be made trading with the Orient. Magellan's route was long, arduous, and so the idea of a shortcut at the top of the globe soon caught hold, the search for the fabled Northwest Passage. The poster child for this act is probably this guy, a violent and bold Elizabethan adventurer named Martin Frobisher, who sailed 3 times into the ice and cold of the Canadian Arctic for gold. Like others, he believed he could reach Asia through the Northwest Passage. In 1576, with 3 tiny ships and 35 men, he crossed from Scotland to Greenland. Storms battered the ships, sinking the smallest with all hands and sending the second ship scuttling back to England in safety. Frobisher, however, continued on, eventually reaching Baffin Island, where he explored Frobisher Bay. There, on one landfall, he casually collected a black rock that at the time was of no import. Now, there are various legends that suggest how this black rock came to be considered gold-bearing, but the most probable is that the English assayers and backers of Frobisher spiked the samples in order to secure fundings for another expedition. Funding's always a problem. In this, they were successful, and Frobisher returned twice to Baffin Island, eventually bringing back 1,400 tons of the black rock. As was bound to happen, it was eventually discovered that fool's gold, not gold, made the rocks glitter. Frobisher fell into disgrace. Today, these same worthless rocks can be found mortared into the stone walls surrounding Dartford Manor. But while Frobisher found only fool's gold, by 1610, tales of abundant whales in and around Greenland and Svalbard led to a whale oil rush, with literally hundreds of ships from Portugal, Holland, England, and France vying for and fighting with each other to kill whales and get their oil. At the time, the monetary return on even one whale was enormous, so it's no surprise that between 1612 and 1800, when the whale fishery finally collapsed, 135,000 whales were killed. With no whales left, the hunters turned to walruses, and soon these too were hunted to near extinction. Greed is often a poor partner to science, and indeed almost none of these early voyages included a naturalist or scientist. Yet I would contend these greed-driven efforts were producing critical cryospheric information, at least with respect to sea ice. Consider this. Frobisher sailed across the Atlantic into waters choked with sea ice in a ship less than 42 feet long. It was hardly more than a small boat. So I think we can confidently assume that he and others were highly motivated students of the ways of sea ice and Arctic weather, as once again their lives depended heavily on that knowledge. The Westerners were also learning about the cryosphere in another way, contact and interaction with the Aboriginal natives. On his 3rd voyage, Frobisher brought back 3 Inuit to England. These Western Aboriginal contacts were fraught, strongly colored by inherent racism. Yet, nonetheless, the knowledge base that allowed Aboriginals to survive in the Arctic, a very harsh country, was being transmitted to the West and would play a fundamental role in later scientific successes. In time, greed gave way to empire as motivation for polar exploration. French, Russians, all important nations competed to be the first in polar discovery and prestige. In particular, the cessation of the war between England and France set up a peculiar condition. The English found themselves with excess naval personnel, yet a global strategic imperative that they be a naval superpower. Without a war to hone their navy, the best next thing was to throw their sailors at the Northwest Passage. So it was that this fellow in 1846, John Franklin, commanding his third Arctic expedition, led the HMS Erebus and Terror and 129 men into the polar mists where they disappeared. What happened? The public back then, as today, loves a mystery, particularly one likely to be lurid and fatal. So between 1848 and 1910, over 50 polar expeditions involving thousands of individuals and now scientists descended on the Arctic, seeking clues to Franklin's fate. It'd be hard to exaggerate the historic impact of such a massive effort on our current state of cryospheric knowledge. As most of you will know, what emerged was that Franklin's ship, shown here in a new TV show, had been trapped and crushed by the ice. While Franklin died of natural causes, most of his men died slow and painful ways, from freezing, from scurvy, from starvation. Today, the Erebus and Terror have been located and are undergoing underwater archaeology, but the fascination with Franklin continues. Ironically, while Franklin's men died because they were unable or unwilling to adopt local methods, many of the search expeditions, lacking the deep government funding that Franklin had, essentially had to go native. For example, Charles Hall, shown here, learned to speak Inuktitut and traveled with his Inuit couple. He became a superb hunter-traveler. But it's not till the end of the 19th century that I think we can point to the first truly scientific cryospheric expedition, at least in the Arctic, Nansen's 3-year Arctic drift experiment. His expedition had in its roots the chance discovery of some debris from the USS Jeannette on the coast of Greenland. The Jeannette, it had been crushed on the opposite side of the Arctic, so Nansen reasoned that there must be an overall transpolar drift. He set out to test the hypothesis systematically and scientifically. On this voyage, meticulous scientific records were kept of weather, ice conditions, magnetic strength, and so on. And his ship, the Fram, shown in the background, was designed using the most up-to-date engineering. But note how he and his crew are dressed, traditional clothing that dates back almost 24,000 years. I think the end of the era of greed and empire might be best illustrated by the last expedition of one of the founders of modern ice sheet science, Alfred Wegener. The goal of his 1930 Greenland expedition was to better understand Arctic weather systems and their relationship to the ice sheet mass balance. To achieve this goal, Wegener planned to put a station in the middle of Greenland, never done before. The name of the station was be Icemity. This is a picture of the expedition ship, and it suggests the transitional nature of the effort. Here's a sailing ship moored to the sea ice, 1930, remember, something Franklin and Frobisher would easily recognize. Yet at the top of the mast, you can see radio antennas. At the bow of the ship, there are dogs and dog sleds, but on the ice in the foreground are 2 aero sleds, propeller-driven snowmobiles, capable in the right conditions of speeds of 100 kilometers an hour. Both means of transport were used to establish Icemity, yet still critical materials, including wood for a hut, failed to make it to the station before winter set in. In a fairly desperate effort, Wegener, Love, and Vilmundsen made a bitterly cold November dog-mushing trip in with additional supplies. Love's fingers and toes were frostbitten, so he remained in the Icemity snow cave with Sorgi and Jorgi for the winter, while Wegener and Vilmundsen immediately headed back to the coast. They never made it. Wegener was found the following May laid to rest in his sleeping bag, having died of a heart attack. Vilmundsen, sadly, was just one more polar scientist to disappear into the clag and mist. Chapter 3, or Act 3, Hot and Cold War. Even as Wegener's 1930 expedition was coming to a close, war clouds were building on the horizon, and a fundamental change in the nature of cryospheric research was underway. The Wegener expedition, purely scientific in nature, had been funded by the German government, which would shortly be in the hands of the Nazis. There was very little interest at government levels in ice sheets, but great interest in weather. Even in that bitter winter of 1930 in the Icemity snow cave, the passions that would lead to World War II were present. Sorgi was a Nazi, Love was a Jew. As World War II erupted, radioed weather reports from Greenland and Svalbard were routinely being used to predict the weather. So it was in 1941 as the Lend-Lease convoy program started, shipping materials from the US to England and Russia, the Allied command soon realized that these weather reports needed to be stopped. They were benefiting the German Luftwaffe more than the Allies. That began the start of what is called the Weather War. Norwegian, American, and British soldiers and sailors fought Germans on the east coast of Greenland and at high latitude in Svalbard. And indeed, it was actually a hot war. People died, and eventually the stations were taken out. Following the hot war, the onset of the Cold War further heightened this awareness as people turned their globes on their side and discovered, my goodness, it wasn't that far across the North Pole where Soviet missiles could come from. Knowledge of how to build radar installations on permafrost and ice sheets, of how to carry missile-carrying submarines could break through the pack ice, all of this gained importance. The polar regions, once remote places of mythical wealth or a stage for heroic deeds, had become critical elements in geopolitical strategies. They could no longer be ignored. National security concerns ensured there'd be research funding from both military and civilian sources for cryospheric research. For example, the seminal work on the mass balance of Greenland done by my mentor and friend Carl Benson came about because Thule Air Force Base was established in order to basically serve as a hedge against the Russians. My own life as a cryospheric scientist has been affected by these forces. I was hired by the US Army and spent 27 years of my scientific life doing cryospheric research under Army auspices. Though little of my research is about war fighting, I would argue it's been awareness at the highest government levels that the US must stay involved in both the far north and far south for national survival, and that has assured that there's been research money. Epilogue, climate in crisis. Where does that put us today? I believe we are starting a perilous new act, like Act 3, where a world at war found that the collective survival required knowledge of the cryosphere. Today we find ourselves in a similar place, but for, of course, very different reasons. The warming climate has produced changes in the cryosphere faster than anywhere else on Earth, and these have very real potential to accelerate global rates of change. They literally threaten our survival. It has become essential now to all of humanity, not just of those of us who live and work in the polar regions, that we track and understand these changes, because what happens in the cryosphere now affects us all. But what about Lincoln's House Divided speech? The most recent polling, which was just done this year, of American attitudes on climate change confirms we remain conflicted. 70% of those polled believe climate change is underway and harmful, yet less than 50% believe it will affect them personally. Until Americans and others understand that just as our Eurasian ancestors, trekking through the mists and blizzards of Beringia, understood that our individual personal survival hinges on understanding the cryosphere and climate and taking action, I fear the necessary action may continue to elude us. Thank you.
Thank you, Matthew. I see now we were a little short-sighted limiting things to 100 years. That was fantastic.
Well, there's two pieces of wisdom. Don't follow Matt and don't follow Waleed. But, and especially because I'm sort of a lightweight after the heavy stuff you've heard here. But at any rate, I'm going to try to tell you a few stories and lighten up something which is pretty heavy, and then maybe we'll get a little bit of heavy at the end. So I was asked to talk about paradigm shifts in cryoscience, for goodness sakes. And this is way too over the top. I want to thank the organizers, the cryo section, the panelists, thanks for coming, right? So I'm going to tell stories, right? And I'm going to have ones that I'm in, not because they're more important, but because I have pictures of them. So be that as it may. I started working on ice in 1977 as an undergrad at Ohio State the summer after my freshman year. And I was working with Ian Willens, and he told me the story I'm going to tell you. I was not there to observe every single piece of it. So the corners may be rounded off, and it makes a better story, right? So you know, if you take a block of ice, there's a block of ice, and you hang a guitar string on it with some weights, you know what will happen, which is that it will move downward through the ice. And here's a cross-section. The pressure is high under the guitar string. That lowers the melting point. Heat flows in there and melts. The water flows around. It freezes. And heat is conducted back through to keep the process going. And if you watch very long, it will fall out the bottom, leaving a block of ice. Right? And it will go faster if you have bigger weights, or if you have a skinnier guitar string, or if you have a higher thermal conductivity of your guitar string. Right? So suppose you are a researcher at a major football university and you happen to work on ice. This major football university at one point had played a football game against the University of Michigan in a giant blizzard. This was called the Snow Bowl in 1950. And suppose your administration says, we are going to bring the alumni back to celebrate the Snow Bowl. We need to educate the alumni and make them happy with ice-themed things. You or the Polar Research Center get busy. What could you do? And what Ian said was, well, if you hang a guitar string with Ohio State colors, and you use the metal high E string, and you hang a guitar string that has University of Michigan colors, but you use a classical nylon string, the Ohio State string has higher thermal conductivity. The alumni will be getting libations and enjoying themselves, and the Ohio State one will win. The alumni will cheer. This is truly wonderful. They will write checks to the scholarship fund. Everybody will be happy, and this is how a major research university works. Okay. For any of you students, I'm sorry if I've disillusioned you, but this is important. You may have gotten a scholarship out of this. So, right? So what do? Ian knew about regulation. When I needed to learn this stuff when I was a student, he said, go read what Hans Weertman said in 1957. What Hans Weertman said in 1957 is, I've been learning about this from Fermi, hat tip to Doug McHale, in 1937. If you go back and read Weertman's paper, he thanks John Glenn for suggestions. He thanks John Nye of the Nye Lecture and Gordon Robin and so on. Very clearly, one of the paradigm shifts in glaciology has been, it sort of started out with heroes coming back from places and saying what they saw. And it turned into, in part, bringing the very best of science and the very best of physics, and now chemistry and biology, and some meteorology, some material science, and you see some of the many names, right? Steve Warren is down front here, for goodness sakes. And so we've had people who have brought the very best science to bear on ice, and they have taken what they learned from ice back to the very best science, and certainly making us a highly rigorous, first-rate scientific undertaking is one of the main paradigm shifts in our field. You have to be good at science to do this, okay? Now, I studied at Ohio State, then I went up to Wisconsin to work with Charlie Bentley. I went down, I dug holes in the snow, and I looked at the layers. We drilled ice cores. We gave the ice cores to the contractor, and the contractor melted them. I was doing structure, I was doing geology, material science. I had my cores in plastic bags. When the contractor realized they had melted our cores, they did not tell me. They refroze them. If you've ever opened your boxes in April and looked at your PhD as little refrozen puddles of ice in the bottom of plastic bags, yeah, okay, so what do? So I went up to Site A with Bruce Cosey and Keith Mountain in the Polar Ice Coring Office. We went back to Antarctica. We got more cores. The camp at Site A did not have an outhouse, and it did not have comms that worked a whole lot of the time. There were 3 of us. If something had gone wrong, Bruce and Keith were going to save our butts, or we were in trouble. And this is true. And what has happened now? If you want to see some of those cores, you go to the National Ice Core Lab. And the National Ice Core Lab is this fantastic first-rate facility, and it happened because some people who are real heroes put a lot of their careers into building it. People like Joan Fitzpatrick and running it, Jeff Hargraves, making it funding and working and making sure it was accountable, Julie Palais, the NSF, the USGS. You go to the field and you're clean now, and you're safe now. And you get what you went for now. You can get help on your GPS, you can get help on your seismics because there are people out there who are doing this for you. And the transition to professional field work that gets the data and gets it home without melting your PhD is surely a paradigm shift in how we do business. We do not eat our shoelaces so we don't starve to death, right? We have cooks. Good heavens. Okay. Right. So I was at Ohio State still, and the community was headed for ice streams, and Bob Binshadler's role, Charlie's, Ian, Doug McHale, we were headed to try to understand how ice goes fast, because that's the key to sea level rise eventually. Ian at the time thought that longitudinal stress gradients might matter, so he told me to build what now we would call a higher order ice flow model. And I built what we now would call a higher order ice flow model. I carried it around in a box under my arm, and I ran it through the card reader. And I couldn't do a thing with ice streams. It did not help. And so I ended up doing a master's on East Antarctica. Ian went on sabbatical, and with John Bolzen's help, we froze my ice stream to the bed and called it East Antarctica. And Ian called this the Palace Revolt. But at any rate, so when I was a student, if you took glacial geology, they told you that till was a really, really hard thing that was smeared class by class out of the ice onto the bed and never moved until they excavated the foundation of the house I grew up in, and we couldn't grow tomatoes in it because the till was just miserable stuff. So at any rate, till was hard. Right, now there were hints, right? So Jeff Bolton had gone in front of a glacier in Iceland, and he kept sinking knee deep in it. And he said, this isn't hard. And he put some markers under the glacier, and they moved, and he said, wow, till is soft. But most of us weren't listening. And there's the ramp again. So Waleed showed you this. This is down on the Saipo Coast in West Antarctica, and there's the upstream B camp. And that's an ice stream. And Don Blankenship went down to the upstream B camp, and he went down with digital seismics. And there were people, Ben Abernathy and Lee Powell and some other people at Wisconsin, who were actually ahead of industry. They were where the leading edge meets the bleeding edge. And Don came back and he said, here's the answer. Your ice stream is sitting on 5 meters of mud, and you would sink knee deep into that too, and maybe neck deep. And, and why do we have ice streams in many cases? It's because there's till underneath. And that came back because brilliant people pushing the edge to the bleeding edge, and a transition to digital, right? So, and I think that sort of a soft bed is a little paradigm shift, not a big one. I mean, Peter Clark and Dave Pollard have explained the transition to 100,000-year ice ages as Ontario running out of soil that it could ship down to the US so we can grow corn in it. And how you get a well-lubricated ice stream. If you were a carpenter and you start sanding something, you get sawdust, you have to blow it out of the way. If you're a glacier and you start eroding something, you get till and you have to wash it out of the way. And so a whole bunch of things on glacial geomorphology and sediment fluxes live on this. But the big paradigm shift has been what Waleed just showed you. It's the shift from a human observer to digital instrumentation, to our ability to see it from space, to see it from the air, from drones, from the surface, from subsurface, from flying around in the water under the ice streams. Right now, be perfectly honest, we are not ready for the flood of data that is coming. We risk drowning in data, and boy, oh boy, is that wonderful. Right? So, love it. Okay, so thank your neighborhood instrument designer. All right, so here's one. Sridhar is a brilliant scientist. He's a brilliant field worker. He's also a brilliant instrument designer. He is at the moment out on the Rutherford ice stream somehow. We knew that ice streams could respond fast, but how fast is fast? And so he had built this wonderful passive seismic system with fiber optic link, and he went down and listened to the ice streams, and they had earthquakes. And then he got more instruments, and he realized that the earthquakes were marching upstream. When the tide changed at the end, 100 kilometers inland, you knew about it in a day. Right? So the question, how fast can ice respond? 100 kilometers in a day is fast. Okay? And we played around with this. We tried to take those data and learn what was underneath the ice, and we were doing data assimilation, and we could turn a few data points into 2 data points. Right? Well, now, if you've seen, I picked out one paper here. I think Brent might be around somewhere. If you've seen what has become of data assimilation and how fantastically powerful it is to take all these data that Waleed showed you and run them into a model in a smart way to find out how it works. This is what we have to do to deal with this flood of data that's coming. And this is surely a paradigm shift in how we deal with this. Okay? So I carried an ice flow model under my arm. I did, you know. I highlighted the ice sheet system model here because Emily Schwanz, who's down here working with Byron Perzak, are using this model with great help from the ISSM team. There are a few sort of world-class models now. And we have world-class models. And when I was a student, we carried them around under our arm. Okay, so this is wonderful. If you go talk to climate science, you talk to atmosphere, ocean, what you find is we need toy models. We need reduced dimension models. We need emulators. We need simple things, but we need that organizing principle on top of the really big comprehensive model. And we finally have it. And I'm showing an ice sheet model, but I just listened to a whole bunch of talks on sea ice a couple of weeks ago. This is coming, snow is coming. There's a whole lot of wonderful things that are being done on making sure we have this hierarchy of models that can do the job. Okay. So a few things that I see. We have brought in fundamental science. We have professionalized field work. We've made huge improvements in data and in models and in putting them together. And we have realized that ice can change really, really fast. So let me just hit a tiny bit more. If you have a model, you need to test it against history. You need to assimilate history to get the future. So, you know, you can do lake sediments, you can do ocean sediments, you can do tree rings, you can do cosmogenics on moraine boulders to find out how much cosmic ray burn they have. I did a little bit of ice cores a long time ago. And you saw this one already from Waleed. 400,000 years ago on your left, today is on your right. This is the Ice Age cycle. And that is obviously paced by features of Earth's orbit. But there's a very interesting thing about the features of Earth's orbit. When half of the world is getting more sun, the other half of the world is getting less sun. The total change in sunshine to the planet is essentially zero, a tiny little bit, but not much. And when half the world gets more, the other half gets less, and the entire world does what Canada does. And Northern Europe. And that's a really, really strange thing. Why should half of the world ignore its sunshine and do what somebody else's sunshine's doing? And the answer is that top curve. And we'll get that out of the way for a second, right? It's greenhouse gases is the biggest reason why this is. You go back and look at history of climate, and you find CO2's fingerprint everywhere. And no matter how hard you try, you can see it. And of course, that if you squeeze it down and you do what Waleed did, this is CO2 today, and this is where we're going under business as usual, this is a big deal, right? This is a little bit of sea level data. When CO2 was high, sea level was high. When CO2 was low, sea level was low, and this is causative. The modern CO2 maintained for a long time puts sea level a little above 10% of humanity. Now that might be slow, but it's interesting. Right? Now, climate change, we do see CO2 makes it hotter, but sometimes it gets interesting. So these are things from GISP 2. Today is on your right, 10,000 years ago is on your left. There's the little ice age, the medieval warm period. They have names because they affected people. We don't name it unless it affects us. And so they have names because they affected people. Not hugely, but enough that you know about it. And you know what's over there, right? This happened. And not much globally average change, but pretty much everybody on the planet got a change in their climate. And the previous slides over here, this has sort of happened a lot of the time, right? This is interesting. Right? And that led to, I think, another paradigm shift, abrupt climate change, and hey, we should keep this in mind and deal with it. Jim White chaired this panel, a fantastic panel, on how do we think about this and what do we do to incorporate this in our thinking. So let me then just finish a little bit shock and awe, okay? You've seen all of these before, so I can do it really fast. The world is warming. The Arctic is warming faster, okay? Where and when snow and ice care about temperature, they are shrinking. So this is snow that cares about temperature in June. You know, you have minus 50 at the South Pole, you might warm it up to minus 45, it's not gonna melt. But when you go and find who cares about it, the snow is shrinking, right? The Arctic sea ice is shrinking, there's March and September. The ice in the soils in many places that have been frozen for a very long time is now melting. And when that melts, things like this happen. And things like this happen as the coast erodes. And, you know, so find the hand of Franklin reaching for the Beaufort Sea. Franklin couldn't get through here, but now you can, right? Okay, glaciers are shrinking. The Greenland ice sheet is shrinking, so as the West Antarctic is going. And so there's some big ideas here, really, really big overarching ones. Warming melts ice, right? Our CO2 is warming the climate, and it will warm it more. The sort of slow warming that we see coming, and slow ice loss that we see coming, and slow sea level rise that we see coming are the best we can expect. If we're really, really lucky, we get warming melts ice, our CO2 causes warming, and that melts a lot of things. Unpleasant surprises really might happen in this. The uncertainties are heavily weighted on the bad side. It could be a little better, it could be a little worse, it could be a lot worse. We could dump West Antarctica and boom, you know. So let me finish here. I don't think that you have ever been more important. You were the Cryosphere section, and there'll be a whole bunch more of you tonight at the reception. I don't think you've ever been more important. I think it might have been more fun when it was a little less important, but it's still fun, you know? Our ability to observe, to explain, to predict is just grown fantastically, and it's grown so because of the paradigm shifts in how we do our jobs, and the people that built the models and the sensors and the ice core labs and that pulled us out of the crevasses. This is really wonderful. What we have learned makes a paradigm shift for everybody else. That there really are abrupt climate changes. There really are abrupt sea level changes. And this matters to how you look at the world. And so the Cryosphere is great. Thank you. I'll shut up.
Fantastic. Thank you again to all of our speakers. I'll welcome our panel up to the front of the room here, and Laura Koenig will moderate for us.
All right. As we get some of our microphones sorted out, I'm going to start. We will have our panel discussion, so please stick around for it. First, I want to introduce our panel members, our speakers as well as our panel members. Our panel members who have joined us, Dr. Jackie Richter-Mengi. She is from the U.S. Research Commission and the University of Alaska Fairbanks. She is an expert in sea ice science and Arctic research. Dr. Larry Hinzman. Larry Hinzman is Vice Chancellor for Research and is a professor of civil engineering, also at the University of Alaska Fairbanks. He is an expert in permafrost research. And Dr. Maury Pelto. Maury is a professor of environmental science at Nichols College in Dudley, Massachusetts, and is the director of the North Cascades Glacier Climate Project. I will also note that he writes for the AGU blog from a glacier's perspective. I would like to say, representing the AGU Cryospheric Sciences section, I am honored that all of you are in our section. These have been some amazing talks. Each of our panel members who have not given a speech is now going to give a brief introduction, and then we will go to questions from the audience.
Oh, thanks. I think I'll stand. Thanks. And I've got to follow Matthew, Waleed, and Richard. Wow, what a lineup. In my few minutes, the thought that I wanted to share with you, kind of looking back at 100 years of Cryosphere, is I would put forward that this is a formula for advancement, and it touches on some of the themes of the amazing talks that we just heard. Environmental conditions, when they actually start having a human impact, we finally get action. And that action is facilitated by money coming into the system. So it is all about funding. Can I have the next slide, please? I have 3 examples to share, and Matthew, you touched on this a bit. World War II, when the US War Department recognizes the strategic importance of Alaska, concerns about Japan attacking Alaska, the understanding of where Alaska lay between Japan and Washington. Next slide. When the US War Department realized that Alaska was of strategic importance, they started feeling like they needed to introduce some infrastructure to Alaska, specifically military infrastructure. But they had the problem of getting goods from the lower 48 to Alaska, hence the movement to have the Alaskan-Canadian Highway, the Alcan Highway, which amazingly, it's an amazing engineering feat, was conceived and took place in the matter of a few years. I think the actual building was a few months. So go figure that that would happen today, not likely. Anyways, with this construction, next slide please, came a problem, permafrost. And here, any of you that live in New England know about mud season. This is like the worst mud season you could ever imagine. Because in the summer, as you peeled away the surface of the soil, you exposed the permafrost and it warmed up and you got problems like this happening. With these sorts of problems, next slide please, there was an infusion of money and we made some significant advances with regard to cold regions construction. So my next example is Arctic offshore oil and gas development. Basically, here you see investments coinciding with high revenue. In other words, when oil and gas, you're getting a lot of money from it, there's money to invest in looking at the environment. And with this infusion of money that comes periodically, next slide please, we've had significant advancements in our understanding of sea ice properties because we need to build these structures in order to operate safely. My third example is the warming environment that we're seeing and the increased access that that is resulting in. The increased access to the Arctic has concerns about economic viability, with regard to shipping lanes. And often when you start talking about looking at resource recovery, being able to perform or do stuff in an area, security concerns follow. Next slide, please. And with these concerns, we've seen significant investments being made in being able to forecast and predict on long-term scales and most recently on short-term scales, because we need to be able to support operations. So circling back to my formula for advancement, combination of environmental conditions, human impact, result in actions because of the support of money. I would contend for this group looking forward, we do a great job about talking about environmental conditions. Next slide, please. We need to focus on what the human impact is and convey those stories. Because when people start to be affected, that's when people start getting behind our science and start making noise about funding going in a direction to help them. So that's my scenario. That's what I say, I'm sticking to it.
I'm Larry Hinzman. I'm the Vice Chancellor for Research at the University of Alaska, and I'm also the President of the International Arctic Science Committee. So that's a group that's fostered international collaborations, and I think has been really beneficial for all of Arctic science. I guess I'd like to, can I have the next slide, please? I'd like to follow up on what this esteemed group has all said, in that there's been tremendous work done by tremendous individuals. We've been blessed with some incredible polar scientists over the years that have made huge advancements. Wonderful polar scientists and incredible students who have really pushed these ideas forward. And from that, we've made great progress. So in the first half of the century, as Matthew said, much of our work was driven by resource development, by concerns about the Cold War. There was exploration and disciplinary science. And really substantial achievements were made in those efforts. And that gave us the basis to understand the dynamics that are going on now and to prepare for this I don't know what the word, traumatic time that we're going through now, this huge turmoil that we're facing. And those tools that they developed gave us a good understanding of geography, climate, and resources. Next, please. And from there, they gave us the tools and the instruments and the progress for continuing that scientific progress. Next, please. So where we are now is that we've undergone, as Richard was saying, we're undergoing a regime shift, or actually a paradigm shift that occurred probably in the middle of the last century, in that we've gone from those disciplinary studies, those explorations, those understanding of geography, to look at more at what's driving the whole system. The interactions among the components, the system drivers, the responses, and trying to understand not just where we are, but where we're going. And it takes a much broader perspective in that regard. So we have to look at things now, coming forward as a system. The first time I saw, in my searching, the first documentation that I saw for identifying and defining the Arctic as a system was from this workshop in 1966 in Lake Arrowhead. And that was where Arctic system science was actually born. And I really think that this was, they did some wonderful work there. I love this statement. They said that, meteorology has always wanted to study global thermodynamics as a system, but there were barriers. Next, please. So they talk about that although the system behaves basically simple laws, it is influenced by interactions of a complexity that has defied quantitative analysis. And that's essentially what we've been struggling with for the last 50 years. And we have to understand this interconnection of components. We have to be able to understand the feedback processes. We have a change in one component of the system, we get a system response, it feeds back, the system changes again, and it's just an incredibly complex dynamic that we're just continually chasing to try and get our hold on. And the final statement, please go back one. Yeah. The final statement I love, this is great, and so this was in 1966. The observational barrier is crumbling, primarily under the impact of satellite observation systems. A single polar orbiting satellite surveys the entire Earth atmosphere system every day. So we've got in 1966, they had the observation problem solved just by one satellite. So yeah, and all it takes is a little more information to understand how wrong we were. Next, please. So I guess I want to follow up kind of with Walid, what he looked at, and what will the next 100 years bring. And there is a dramatic change in where we've gone and where we've got to go. Please advance. So despite what they said in 1966, we're still limited by observations. We have to develop the predictive capability, that understanding of the dynamics, so that we know what the trends are in the major systems. We know the air temperature is getting warmer. We know that permafrost is thawing, glaciers are melting, ice sheets are degrading. But we need that second order variables. We need to understand what wind loads are doing, what snow loads are doing, what water resources are going to be, and there's all those other dynamics that are really important to our society, and that's where we really need to be investing our efforts. Next, please. And one more, please. And the other thing that we really have to focus on is we really need to learn how to mitigate and adapt, and that's the huge challenge before us now. We're in a traumatic period. We really, really are. As Waleed and Richard both showed, for the last 500,000 years, for the most of the period, we've been wrapped up in an ice age. We've been in a glacial period. And I don't know if you noticed it, but the temperature between now and those glacial periods is not much. It was only between 4 and 8 degrees, something like that. It's pretty small. And we've already seen 2 degrees warming in the Arctic, and so we can only imagine what 4 degrees warming could bring. If 4 degrees cooling puts us into an ice age, what does 4 degrees warming do to us? So with that, I'll end. Thank you.
So I'm Maury Pelto. I'm the U.S. representative to the World Glacier Monitoring Service, and it's kind of one thing. I want to talk about you, the scientists, more than some of this other stuff. And I'll do it by looking back a little bit. First of all, it's strange. I work at a small private college, and so the World Glacier Monitoring Service has come to the position where they feel like it's more reliable and better continuity to have me do it than the government. And so you never know where that opportunity is going to come. So if we take a look back, Richard had mentioned Ian Williams, and so I wrote a letter to Ian, way back before there was email, asked for an internship, and he said no. But it wasn't just no. He had a reason. He said, you're not a fit for what we want to do. I'm not going to be able to deliver on what you hope to accomplish. I really wasn't sure what I wanted to accomplish necessarily, but I think Ian was right. And so what that kind of taught me is that, there's a place for each of us. We have to do what we're good at. We have to recognize what we're good at, figure out where we can fit, and then deliver on that. Back, 40 years ago, we could have fit every glaciologist in the world in this room. Today, we can't fit every glaciologist that has worked in the last decade just on Helheim Glacier in this room. Now, this expansion is a really cool thing. I mean, I can look around the room, I see at least 15 people that I have worked with in the field. But why it's happened is we've heard. We're responding to an epidemic of cryospheric losses. And that's our challenge. So here, you can see it. World Glacier Monitoring Service, annual mass balance data. You have to be a reference glacier. You have to do the same thing for 30 years. So when I was sitting in a room, there was Gunnar Ostrom from Norway said, there's nobody that is monitoring glacier, more than a single glacier in a mountain range across anywhere in North America. Somebody needs to do that. And I thought, okay, I'll do that for 50 years. And I've done it for 35, so I still haven't finished that. But that was my niche. I thought that's the ground truth. I then hear a couple years later, MODIS is going to come out. It's not even launched yet. And Dorothy's Hall is talking about making a snow map of the entire United States every day. And I'm thinking, what? That wasn't me. That wasn't where my strength was. So where is your strength? What can you do? You can see how to get things done. And where can you see how to do them? And so that's what I want you to think about. Because as has been said, we really need you. The opportunity is there, and it's really urgent. Now, one more slide, maybe two, but there is some gold in their old data. Really carefully done data. On the left is the Taku Glacier, 500 mass balance measurements in the summer of 1984. It's hard to see what it shows. It's colored pencil because, we didn't have much else, to create stuff like this, and this is how Gunnar Ostrom, suggested I try it. So it's good data. Spatially, did you know exactly where you were when you did your measurement? No, not so great. Chris McNeil went out, Taku Glacier, 2016 GPR, it does the measurements, it uploads right into a spreadsheet right away, you know your location, you know the depth, it's all great and easy to work with. Doesn't make it better data necessarily. So remember, some of this old data, it has restrictions, but also has value. And just one more, I guess, would be, I'll finish with the slide. No, skip that one. Yeah, so just some old velocity data from the front of tidewater glaciers in Greenland. On the left is a peak Sirmium, that's from 1948, and then the Jakobshavn, working up there in 1985 and 1986. So we're drawing these little arrows of velocity. The length of the arrow in pencil is the velocity. There's a lot of points here. We spent countless hours doing this. And so maybe some of you have used this, maybe you haven't. But there's countless old data like this that has real value. It was collected professionally. But I happened to work in the field with the person who developed Microsoft Excel. But at this time, we didn't have that. And so it wasn't so easy to put all the data in a nice, easy way. So some of the work you're going to have to work with. But I really look forward to seeing, and I do look forward to every day down the poster hall seeing what you're doing.
Great. So just some logistics. I'm going to ask the first question, and then we will pass the mic out to people in the audience to ask questions, and then we'll also pull some from social media. Amazing panel. I have really enjoyed celebrating our last 100 years, and I'm wondering, where did we fall down in the last 100 years, and what should we learn from that?
So one thing I've heard from a number of people, it's not going to be universal, but an underutilization of the local population in particularly in alpine glacier research.
Yeah, I think the other thing is our communities have stayed a little more separate than they need to be. So the terrestrial snow community often isn't particularly connected to literally the sea ice snow community and so on. So breaking down those barriers, that's been a bit of a problem, and it would be great to see that disappear.
I guess I'll say from the satellite perspective, it's tempting to watch. This was a big deal with the sea ice minimum. Holy cow, it's getting less and less, and I think more energy, and it's happened more recently. When you first see it, you think, geez, this is, but more energy in the why, what are the complementary processes, how can we understand it better, and what does it mean for the future? So while I think the satellites have been a tremendous boon for us, you gotta keep your theoretical skills sharp, and I think it can be tempting sometimes to let those lapse a little.
I think to add to that, not necessarily where we've fallen down, but where we might fall down with, satellites and the amazing amount of data is actually boots on the ground. As an observationalist, I would argue that you need to get out there. I mean, even if you're, largely doing models or you're studying satellite imagery, if you get the opportunity to go to the field that you're studying, go and see it, because when you go and see it, it really brings it home. And that's also another reason why to, really involve local communities as well. But get out there. It's life-changing.
I don't think we've done a good job helping our communities prepare for the future, in that we really knew the climate was changing in 1985. There was really good solid evidence then. And since then, many of our communities have really struggled and suffered with the consequences. And we've known this is coming, we still know it's coming, and we haven't really done enough to help them prepare and adapt.
Jackie made some really important comments on diversity in the night lecture. You should go back and listen to them. The field needs diversity. So just to point it out, this panel will never happen again. So, and then I think to build on what Larry said, The Nobel Prize in Economics this year was given to two people. One of them was William Nordhaus at Yale for showing that if we use our knowledge about climate change efficiently, we get a bigger economy as well as a better environment than if we ignore our knowledge. And this goes on what Larry said, using our knowledge makes people better off. We have done really well at scaring people. We have not done really well at showing them how they can use this knowledge to help themselves.
Question from the audience. Yep, speak loudly.
So this is actually a question initiated by Jackie's comment that research in cryosphere has benefited when there's a clear payback for it. Perhaps then, following up on what Richard just mentioned, do we need to be better about describing the cost of not improving our understanding, the negative cost of ignorance?
Yes, so the question is, as Jackie pointed out, that we need to understand the financial consequences of our science. You want to speak to that?
Yeah. Given what we know right now, there is a reasonable chance that a high emission scenario will give us 5 meters of sea level rise rather than 1. There is a reasonable chance that that will not happen. A planner faced with 1 meter or 5 in the next 100 years can just throw their hands up. The research to cut off that long tail or to fill it in, depending on what the answer is dirt cheap compared to the cost of preparing for it. We are just in the noise when it comes to real costs of what really happens. So yes, I think we need to be, if you really want to save people money, you do the research to narrow the uncertainty bounds, because honest uncertainty bounds now are so huge on some things with those bad long tails.
I would also say one of the efforts, if you're going to look at causality as a reason to motivate, either positive or negative, one thing I would issue to those of us in the field, a coordinated effort goes further. It's Horton Hears a Who. Basically is trying to look at what are the stories you want to tell and have people telling those stories everywhere so that they get amplified, and then you start getting people behind the request for funding. I mean, it all comes down to convincing somebody that it's going to be good for them, and the more people that think it's going to be good for them, the better your chances at going. It sounds a little cynical, but that's the way I think it works.
All right, Amelia, do you have a question from social media?
This question comes from Alan Pope. How do we build computational skills and future skills in our cryosphere community?
So sorry, Alan, but I'll turn it around just a little bit. I would say that I guess I tend to see our computational skills as outpacing, going back to what Jackie said, our understanding of what we're computing about. And so let's keep pace. I really feel like, when we look at computational abilities, they just keep going up, and I'm not too worried about that trend. I am worried about our ability to, stay out there in the field and understand really what we're modeling.
Yeah, I would amplify that and actually build on what you said. Each of us has a niche of some sort. Frankly, I'm lousy at computational skills, but I've spent an entire career working with a magnificent snow modeler. Okay, he goes to the field, sometimes with me, sometimes I work on the model with him. So not everybody in here needs the computational skills, not everybody needs to be a polar hero, but they need to form connections across the board and thereby become stronger.
I think I disagree just a bit in that I really do believe that when I was young, there was a huge national investment in educating the masses, and it seems like we're getting away from that. And I feel like we're leaving a lot of really brilliant minds, as Jackie was saying earlier, a lot of really brilliant minds on the table. And so I really do think there is an essential and critical need for investment in education just across the board.
Yeah, and hi, Alan, how you doing? I hope you're doing great. So those of us who teach don't really know what most of our students are going to do for their jobs. I'm in a geosciences department, and some of our students will be geoscientists, and most of them probably won't. And so we all try to do soft skills, communications, getting along with each other, and every university and every college claims they do that, and some of them do it pretty well. We're really comfortable at content knowledge. We can speak on what we learned when we were students. You push the professor button and we profess, and it works fine. But we really do have to think about the transferable skills. When the student switches from our field to something else, what are they going to do if it's not in communications? And a whole lot of that is going to be something quantitative. It's going to be GIS, it's going to be coding, it's going to be remote sensing. And so we need to think a lot of our departments making sure that our students have somewhere that they can go if they decide they're not going to do what we taught them.
Question from the audience? Okay. Yes. You can speak up loudly. Stand up and speak up.
So I'm a modeler and I'm interested in ice sheets and glaciers. And so, question of the value of modeling. Are we actually going to, looking into the future, narrow those envelopes around those very scary looking sea level curves, let's say? Or are we actually going to simply identify better where that uncertainty comes from and potentially even extending those tails? With the data we're getting being very specific to the now and here, the natural timescales for ice sheets, for instance, being very long, can we expect to narrow those uncertainties?
Okay, so if we didn't hear the question, I'll very much simplify it as, what our models are predicting and how are we going to narrow those uncertainties with the data that we have now?
We have to find out, and you're going to do a lot of it, right? So we do not know, really. There's fracture involved in this point. And back when I was taking material science classes at Wisconsin, our professor said, do not ever get yourself in the situation where professionally you have to accurately predict a fracture, because you will fail, and then you will get sued, and you will lose your job, and it's a really bad thing. So, but at least we should be able to tell well where the uncertainties are, where the risks are. I think we will narrow those uncertainties. I really do. And I think it's partly because of what you've heard all the way across here and what's sitting out here.
I would agree. I can go back to 30 years ago, sitting in a room with Richard and thinking where the models were then and seeing where they are now. It's an incredible revolution. It's been built by all the things we've talked about, but that gives me confidence that you guys are going to help us get there faster than we think.
I agree too that I think the uncertainties will be reduced, but I suspect between now and then there'll be times when they increase. I think we will see things, as we have through what Richard has indicated and some of what I showed, that challenge our thinking, and we realize, whoa, we don't quite have it, or this is different than we thought. But that's the evolution of science, and I think there'll be, blips on the curve where uncertainties go up and then down, but I think there'll be a trend where we do converge. And that's true not just for ice sheet modeling. I think that's the case for climate, weather modeling, and others.
And I think that one point that Waleed makes with regard to, when work is being done is you've got to let it take you where it goes, or, let it lead you, your work. I mean, I think oftentimes when we start something, we assume something, and we get married to that assumption. And we need to be able to say, I was wrong, and look at something else that might be the actual explanation. I think that iteration will actually help us get, a higher degree of certainty. Yeah, draw up a contract with you and your assumptions.
Right, we'll take a question from AGU's President-elect, Robin Bell.
Great panel, thank you guys, this is really fun. What I've been worrying about, and I worry about every time I drive down the road near my house, which is like 30 miles away from the ocean, and I don't live in New Orleans, I live in New York, and I see houses that have been built up an entire floor because of the storm surge. I start to worry, and then the communities ask me, so dude, what's going to happen with sea level. I realize I'm not quite sure we're making that connection with the science. We're trying really hard at cryosphere science, but those communities need to know, well, how's the shorelines going to respond if they're sinking, if there's GIA, what's the gravity, how's the ocean warming? How are we going to get over the big problems we have and everybody else and really give those people the answer they need?
You know, it's interesting. So, you know, we've been putting that information out for a long time, and you know, there's the difference between the information people need and the information people want to accept. And there's almost a dogmatic belief system that we have to get past first. In that, you know, there's little question to anybody that the sea level is rising, but you know, North Carolina has made, or South Carolina has made regulations against considering climate change in their zoning laws. I mean, so we have to get past that dogmatic, almost religious belief to accept the changes before we can respond to them.
Yeah, that's a great question. One part of what I do is spend a lot of time in villages in Alaska. Excuse me. And step one is listen. You know, we're not very good at listening. Yeah, we're pretty crappy at listening. So when you get in there, and when we go into these villages, the last thing anybody wants to hear is us lecturing to them. You know, they've got their own problems, and you know, it's true, sea level may be a problem, but probably meeting, you know, the food purchase might be as well. So step one is to listen. There's a photographer I've been talking to, he's got listen tattooed on his forearm. And I really think maybe that's the entry point. We have a lot to say, and we have said it, but we have to figure out how to get it received. And I think that might be step one.
So I'll go one step further and say, yes, first listen, and step two is communicate in a way that will be received. I think there is too much, whether it's I'm the scientist and you just don't understand, it's coming, or just a terror, you know, where people, like Richard said, throw their hands up and say, well, what am I going to do about it? I think there is something, a lot of you are familiar with SEARCH, the Study of Environmental Arctic Change, and there are action teams. I co-chair the Land Ice Action Team, which is focused on really integrating stakeholders and the scientific community so that, you know, a lot of us are going to the National Adaptation Forum because we want to hear what people are thinking about in terms of adapting to sea level rise, to get to Robin's point. So I think listen, understand, and speak. Take that information, synthesize it in your brain, and speak back to people in ways that speak to the things they care about and would be receptive to.
And part of that communication is incorporating others that can communicate in a different way. I mean, I see in the first two rows we have some artists. We have Diane Burko, we have Jill Pelto here to communicate. We have comics. I talked to John Cook earlier today, great at drawing little cartoons. You know, there's different ways to do that communication. We don't have to do it all our sciencey way.
I'm going to bring one of our questions from our list. Has there been a single unifying theme the past 100 years for Cryosphere? Should we have one, or do we need one?
Borrowing from Richard, I'd say the unifying theme and the one we need is expect surprises. I think that's really it. The more we look, the more we get surprised. We figure it out as we go, but that's just always been there.
One thing that has served us well is that we've been ready to observe it. It may have been a surprise, it may not, but we knew where to look and we were kind of ready to see it.
I mean, in some very real sense, science has never thrown away the useful parts of scientific discovery. Newton was wrong about really tiny things and really huge things and really fast things, but we're applied Newtonian physicists using fantastic quantum mechanical and relativity-enabled tools, but we are Newtonian physicists. As we learn, the frontier keeps branching, and it keeps going into corners, and it keeps going into interactions with people, it keeps going into interfaces and ecosystems, and what we have to do is keep a world where we can have geeks who want to count photons, yet we respect the people who are out in the community making this useful. And what has really happened to us is this broadening of what comes in our purview, from something which was very simple, find out what the ice is doing, to making it useful. And to keep the core of finding out what the ice is doing and respect that while respecting the people who are out on the frontier making it useful is probably our biggest challenge at this point, and keeping the funding and the community in place that respects that and does that.
Osa?
Okay, I would like to hear your perspective on if this is the golden age of cryospheric science. I mean, Mauro was talking about how 30 years ago, all the glaciologists in the world could fit in this room, and now we barely have the people who study Helheim. But what would it look like in 30 years? And I say this, I mean, right now, the cryosphere is changing so fast, but the rest of the world is catching up, and most of the people live in the mid-latitudes. And when those changes, if we continue as projected, aren't our intellectual power is going to be needed there to deal with problems that are more immediate for the populations there. So I'm just curious about your thoughts on this.
So I don't necessarily think this is the golden age. I expect it's still going to keep getting better and better. I mean, the Arctic is always going to be a beautiful place to work. I mean, it's wonderful to get out there. It takes strength and joy to be there, and the tools that we have now are just remarkable compared to the tools that we had when I started working 30 years ago. I worked with a watch and a compass to find my way across the tundra, and now we have GPS, and it's amazing. I think that there's so many other incredible benefits that we've got now, and I don't know, I'm just incredibly enthused and excited to see what the next 30 years bring, but I don't think we've reached the golden age yet.
Yeah, that prediction is really a bad thing to do. So I have no idea if we're in a golden age, but what Richard said is absolutely true. What used to be a community for which we had a very sharp and distinct boundary no longer is. So I think what we're going to see is it's going to be harder to tell if you're a cryospheric scientist or just need the cryosphere in what you do. Perhaps the golden age is coming. A lot really is what you define as golden. If it's big data, the golden age was certainly not the historic swath I covered. On the other hand, if you want to sledge across the Arctic, maybe that's past. I don't know. So it's really how you want to define golden age. But I think our community, in 30 years, will have very blurry edges, and I think that'll be a healthy thing.
Yeah, this week it does seem like the golden age. You're here, you're talking you see all the posters, the science is great, it's fantastic. And then you go into the field. And in my case, the field isn't very good. The air is filled with smoke, the glaciers are disappearing. So that doesn't feel like the golden age.
I think we've been filled with and will continue to be filled with golden ages. I think there was so much to discover. I think the early observations in the field and just looking at snow and understanding crevasse behavior and then developing modeling capabilities, and now we have the satellite observations. I think it's going to keep getting better and better. I don't think 30 years from now we'll look back and say, man, wasn't it a good time in 2018? But I do think the opportunities and the information keep getting better and better. So we're getting golder.
That sounds very nice, Waleed. I would also say, I think that will continue to be true with regard to the cryosphere is the fact that it is a great way to convey the warming environment. Really everybody, it's very fundamental for people to understand that ice melts when it gets warm. So it's a really good vehicle for helping provide the indicators. And I think that that will continue to be the case because so much other is more complicated than that. So keeping that as the tip of the spear, I think will keep Cryosphere, at the tip of the spear. Maybe that could be my quote, Rick. Keep 2018.
Questions? Will you come up?
Yeah, I was just wondering, we've heard today a lot about making more of an effort to bring underrepresented groups into glaciology and cryospheric science, and we've heard about maybe trying to involve women and bringing indigenous populations, but with the knowledge that we have potentials of sea level rise and impacts on areas around the coastlines, maybe there's an opportunity to do some targeted outreach to groups in places like Florida, Puerto Rico, and bring in some of these underrepresented groups. And then by doing that, that could help also interacting with local communities that are actually going to be impacted by what's maybe down the pike.
I think that's absolutely true of communities that feel something. There was a study after the hurricanes in the summer, the surveys of people who thought greenhouse warming was largely anthropogenic or something else, and before the hurricanes there was a low number, and after it really hit home. So I think people who feel things will be engaged from the standpoint of climate and weather. For cryosphere, it's a little tougher. If you think about the sea ice aspect, people aren't feeling that. If you think of the sea level aspect, it's inching up. It's millimetering up. So it's a little harder, I think, to make that direct connection, but nonetheless, I think it's worth doing, and I think it would be successful.
One thing I would convey is something I heard yesterday in a town hall with regard to diversity and inclusiveness. It's that to keep in mind. I think it's a great thing. Your suggestion is good. You have to, again, the whole issue is not just bringing people to the table, it's retention as well, and that's where this whole issue of the work environment comes in. I mean, you have to make a work environment that's welcoming. It's a meal that they want to eat. I think there was a really great graphic that I think a fellow from the National Science Foundation showed, and when we sell the program, it's a boardwalk towards Oasis, and then the reality for many underrepresented peoples, it's a rickety boardwalk towards a stormy sea. So, trying to rectify that will actually not only bring people, but keep them, smart people, brainy people in the sciences.
Yeah, the question was from Julie Palais. Julie was doing her master's with Ian when I was doing my bachelor's, and I have learned from her for a very long number of years. Hi, Julie. Thank you. You're absolutely right. And we have, so the Thwaites effort that NSF and the British Antarctic Survey and others are involved in now has been doing education and outreach. A whole bunch of us spent last week on the phone with schools all over America, and also all over the UK. And Thwaites was the entree. And they wanted to know about climate change. They wanted to know a little bit about penguins, a little bit about polar bears, a whole lot about climate change, a whole lot about their future, a little bit about jobs, a little bit about global warming, a little bit about the economy. And this was the entree. It opened the door. And once you got in the door, it's all there. So if nothing else, people appreciate just how beautiful this is. They appreciate that there's a signal there's something that we can use, and once you start from that, you can go to all the other stuff that matters. So yes.
So one of the things that SEAN does is we host every 2 years, host the Arctic Observing Summit, and in the past several years, many years, we've really tried to engage indigenous populations in we hosted one in 2016, and 10% of the participants were from indigenous groups. In 2018, we had a smaller but still significant proportion. And we're really trying to use their participation, their understanding their driven desires to address these issues to help us design the systems better. And so I think from that engagement, that introduction, it really does help those groups become involved and stay involved. And I think we're going to continue to do that.
So I'm going to pull one of our questions too as we talk about the diversity issues. One of the things that I noticed when we look back, we often talk about single author papers or dual author papers throughout the talks. And now we talk about things like IMB and groups. So what are the pros and cons of how we did science in the past, which was more attributed to one person, versus group science of today?
Yeah, I wouldn't use the word pros and cons. What I would say is these are different modes, and they're both really interesting. I can look to myself, you know, on first few papers, one, maybe two authors. And you look through my career, 6, 7, 10 authors. I think on Sheba, then I forgot, you know, 30 or 40 authors. But now, at this stage of my career, I'm going back to smaller author papers. The way I look at that is it's a question of what it is you're trying to do at that point. If you're on big data, you know, maybe that's not a 2-author paper. But if you've got, as what Richard said, subject matter knowledge, and you've been thinking about something for a long time, that may be these smaller author papers. So what I would urge people is to not think of it in those terms, but rather, what is it you're trying to get done? And then the right number of authors is what you should get.
And I think that's reflected in what you just said. I think theoretical papers early on came out of the minds of a few really bright people who've been thinking long and hard about something, and then you get something like Sheba, or you get the IMB effort, or you get something that requires a lot of people to dig into and understand. There's a guy who works at my institute who has one of the most highly cited papers, and I thought, wow, that's really interesting. But then I saw there were 69 authors on it. So I think citations might be a pro. If you're looking for that, get a whole bunch of authors and you'll get cited a lot.
Actually, I really do hope we transition more to multi-authored papers, and that I really do sincerely believe that the big issues on the horizon are system-level questions. And system-level questions require experts who can address multiple components and can work together collaboratively. And you know, if the big issues, I think, for us where they can make the really great progress is right at the interface of disciplines. And that's where I really think we need to get these collaborations, these partnerships built, so we can make those strong scientific advancements there.
You speak of uncertainties, potentially growing uncertainties, surprises, admitting when we're wrong. Yet these statements, although they're fine in this room because that's what we know, when we make those statements to a broader public, there are certain people and policymakers who prey upon those. Do you have suggestions for how to better convey the uncertainties that are within our models to a public that goes, wait, they don't know?
I heard a brilliant one yesterday. There are no climate deniers in the reinsurance industry. And that's actually hugely important. So the people who actually are betting on the future are betting that we're right. And they know this, and they also know that the long tail is not their friend. It is very much easier to break something than it is to build it. Right? You probably have a cell phone in your pocket. I know I have one in mine. And you know what goes into building a cell phone, and you know what it takes to break it. You drop it in the toilet, and you know, that's unless it's a new one, in which case it's a hammer. We're not going to build Eden by cranking up a whole lot of CO2, but we can break a whole lot of things. And so the risk management side, the professionals in risk management say, take this serious, it's real.
The other thing that I've found works is framing it in terms that people can relate to. Richard talked about the reinsurance industry. The military as well, an inherently conservative organization, knows that their Tactical and strategic success depends on anticipating and understanding threats and risks. Something I often do is I'll show the temperature graph and I will show the S&P 500 alongside it, or the Dow. And I will say, I'll take the Dow, it's only 30, you don't have to keep track of it as much. There are, the Dow curve, it goes up, it's got wiggles in it, and when you tell a business person, do you think the market is done? Is this curve going to stop because the last 4 months look like this? They kind of nod their heads. Or if you say, well, there are 30 elements to the Dow. If one of them goes down, that's the same thing as a cold winter in Nebraska. Are you going to say, oh, the Dow is done, right? So I think framing things in ways people understand and can relate to. And I love doing this. I'll show them the curve and not tell them what it is, and get a reaction absent of what that information is. Do you think this is going up? Do you think it will go up? Do you think it's done going up? And once sometimes I'll show them temperature, sometimes I'll show them the Dow. And once they sort of see what it is, there's a different response. And I think framing things in a way that people relate to. People don't really understand the data distribution and why Nebraska might be different from Argentina, or something. But they understand why, why some stock in some business sector may have behaved one way and another way, but the market does what it does.
Great. Well, I think with that, before I thank our panel member and speakers, I want to remind you that this is just the first of our 100 years. We looked back 100 years this year in 2019 in San Francisco. We'll have the next 100 years of Cryosphere where we will get to talk about what our future will look like. Thank you again to all of our panel members. You are truly gems within our section, and thank you for all of your opinions and your history and insight.